Just FYI, OD227 runout looks like missed distance of 232 meters. Over.
232 meters?
That's correct. Less than the divert.
Roger. We can expect a brief signal dropout when we switch to the TLGA.
We're at 3 minutes to entry. At this time, MRO should begin picking us up. But remember, we won't get that data for a while. It's got to store it and then send it back down here for us to decode. We're still seeing heartbeat tones. Everything looks good. Spacecraft should be up to 5.6 kilometers per second. Entry.
The EDL team is reporting that the latest runouts, which is using the latest nav, our best guess of where we are, show us that the best guess of our landing target location is about 232 meters from the landing target. So, looking good so far. We're continuing to receive heartbeat tones. Everything looks good. We're about 90 seconds from entry.
Flight dynamics EDL phase.
Go ahead, phase.
That last solution was with 227 or OD228?
That is OD227.
Thank you. You guys have now OD228 in your possession?
There will be no 228 for us, phase.
That's just fine because the difference is
1 minute to entry.
Within spitting distance.
Affirmative.
The vehicle will switch antennas shortly. We'll have a short dropout when that occurs in the tones, switching to a tilted antenna that will be used through entry.
As you come up on entry, we'll expect a 2 to 3 second outage in the X-band signal as we switch from the ELGA to the TLGA.
We're switching to TLGA, signals dropped, and it's...
We just saw the signal drop. That indicates we changed antennas.
We're seeing heartbeat tones again after the switch. Things are looking good. Yeah, tones back again. Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do.
Back to heartbeat tones.
We're standing by for guided start of guided entry.
Nav can see the engine atmosphere in the Doppler.
We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way into the target. It is starting its first bank reversal. heating and peak deceleration. It is reporting that we are seeing Gs on the order of 11 to 12 Earth Gs.
Flight GSA.
GSA flight go.
We are processing data from Odyssey.
Tank reversal 2 is starting. We are now getting telemetry from Odyssey. Tank reversal 2 complete.
Copy, tank reversal 2 complete.
Thanks.
Standby flight. We have a connection, but we actually do not have any data yet.
Copy.
We can expect some intermittent contact at this time as the signal gets
There we go.
increases to
Tank reversal
respective
3
levels.
starting. We are now seeing telemetry from Odyssey.
Okay, copy.
And visualization is updated. Enter heading alignment.
There it goes.
At this time, Curiosity is no longer trying to control how far it's flying downrange, and it's just heading directly for the target.
End of range control, air use minus 1.2 kilometers.
Minus 1.2.
1.2.
The EDL team is reporting that we are, that things look pretty good at the end of range control. We have converged a lot of the error, and we should be heading for the target.
Flight EDL, TDS warning is okay.
Copy.
Power on.
We are seeing a tone from
The 1 gigahertz.
indicating that we have seen heating on the heat shield through the MEB instrument. Everything looks fine. This is as expected. During this heading alignment phase, we're flying almost horizontally like a plane. We're going about Mach 2.4 at an altitude of 17 kilometers or so. Vehicle's reporting heartbeat tones again, indicating that everything is fine during heading alignments. We are standing by for straighten up and fly right and parachute deploy. Vehicle's continuing to decelerate. We're down to about Mach 2. As a reminder, we should have parachute deploy around Mach 1.7. We're at 15 kilometers altitude.
We've begun entry balance mass jettison. The predicted mid
Stand by for parachute deploy.
downrange is 1.597 kilometers.
EDL Labs, Odyssey Systems on EDL Labs.
Parachute deploy. Parachute. Thrusters have been re-enabled. We will control our attitude on shoot. We are decelerating.
Risk mode under
Our 10 kilometers
parachute
decelerated
are 20
and
to
descending.
30.
We are at 150 meters per second.
Dynamics phase. Come back again with risk mode dynamics.
Risk mode is nominal.
We are at 9 kilometers and descending.
Downrange.
That filter converged with a velocity correction of 0.7 meters a second.
We've acquired the ground with the radar.
An altitude of 8 kilometers.
Feed shield has separated. We found the ground.
Expand tones due to earth occultation as expected.
We're standing by to prime the MLE engines in preparation for powered flight. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending.
Flight EDL, we've got some Tweedo warnings. It is in battle short mode, so it should power through.
Director of Communications at this time. We may have lost it already. We're down to 86 meters per second at an altitude of 4 kilometers and descending. We've lost tones from Earth at this time. This is expected. We're continuing on Odyssey telemetry.
Ground solution equals minus 10.8 meters, vertical velocity of minus 80.
We are priming power satellites and start enabled, standing by for back shell separation.
Signal to Odyssey is still strong.
We are in powered flight. We're at an altitude of 1 kilometer descending, about 70 meters per second.
Signal to Odyssey remains
Down to
strong.
50 meters per second. 500 meters in altitude. Standing by for Skycrane.
Constant velocity accordion nominal. Altitude error 5.9 meters.
We found a nice flat place. We're coming in ready for Skycrane. Down to 10 meters per second. 40 meters altitude. Skycrane has started. Descending at about 0.75 meters per second as expected. Expecting bridle cut shortly.
Signal to Odyssey remains strong.
Tango Delta nominal.
Yep. Eagle.com configured.
Review stable.
Jet telemetry.
Review stable.
UHF is good.
Touchdown confirmed. We're safe on Mars.
Time to see where our curiosity will take us. At this time, flyaway should be complete. Descent stage is at safe distance. We are continuing to receive telemetry from Curiosity. We're safe.
Getting data from the surface of Mars.
ASCAM sequence is kicked off, waiting for images.
Heads up, folks. PL out, signal to Odyssey remains strong.
Flight EDL images are starting to come down. We're beginning to get images.
We got
from
images
Odyssey.
coming down, folks.
Eagle.com configure standby for images. We have
See thumbnails coming down.
Odyssey data is still strong.
Odyssey data is very strong.
Odyssey is nice and high in the sky.
At this time, we're standing by for images.
Thumbnails are complete.
Got thumbnails.
Poland is complete.
It's the real. It's the real.
There we go. We can see a real image. We are wheels down on Mars.
Oh my God.
We'll do a proper hug on the other side.
Keep watching, guys. Keep watching the screen. There's more stuff. Any minute now. No. 2:56.
Okay, okay. So here we are.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought. surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been launched, dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical diversion. We fly off to the sun.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity. Getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover, it could damage mechanisms, and it could damage instruments. So the way we solve that problem is by using the sky crane.
20 meters above the surface, we have to lower the rover below us on a tether. It's 21 feet long, and then gently deposit it on its wings, on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. You must cut the bridle immediately and fly to the descent stage to a safe distance from the rover.
Are we good? All right. I think we're ready to roll. Welcome, everybody, to the August meeting of the Ottawa RASC. And what can I say? What can I say? What a week. I hope you enjoyed our little video there. And I just want to give my sincere congratulations to the thousands of men and women that were involved in getting our most advanced human presence on Mars to date. I think we're going to see some spectacular stuff from the Curiosity rover, and wow, pretty exciting stuff on that touchdown. Talk about daring mighty things. I love the way they ended that video. I know Al's going to give us an update on the landing itself and the latest goodies there, and I've encouraged Rolf to add a little statement or two when he comes up and talks about his observations, because his company was actually involved in producing some of the components for that vehicle there. So my hat's off to everybody involved with that, and I'm looking forward to an exciting 2 years of Mars exploration. So good stuff. All right. Well, yeah. Awesome work. All right, tonight's program, we've got a bunch of interesting talks for you there. As I mentioned, Al's going to give us his typical astronomy news update with an emphasis on Mars there. Gary's going to tell us what's in the Ottawa skies. Exciting times, too, because, as Gary will let you know, we've got the Perseid meteor showers happening in the next couple of days. They're peaking. And I'll throw in my 2 cents worth. I've actually been taking some pictures last week before we finally got the clouds and the rain with the moon up, and trying to catch some of the Perseids, because even with a full moon up, I've seen a number of brilliant Perseids in the sky. They're 30 degrees, 20 degrees away from the moon, and they've been spectacularly bright, even under hazy skies with a very, very bright moon. So I don't know if that bodes well for the shower coming up, but I'm crossing my fingers there and hoping for some clear weather. Rob is going to talk to us about LED lighting, LEDs in astronomy, and how they affect your night vision. Eric Kuyela is going to give us a talk about or an update on the outreach. We're going to have a series of good observations there. We've got some good images there. And then Tim. Yeah, Tim unleashed in Hawaii. He's going to talk to us about his adventure to see the transit of Venus on Hawaii. Tim, I meant to ask you too, I mean, at the time you were gone, I got an unconfirmed report of some crazy Canuck putting a stale breakfast sandwich on one of the mirrors and then sitting on it trying to make a panini. You wouldn't know anything about that, would you? No?
I have no recollection.
No, okay. That's good. We'll keep it that way. And finally, Jim Maxwell. Like that panini did, right? Yeah. And then finally, Jim Maxwell will give us an update on the RASC project known as SmartScope. I'm looking forward to hearing that. All right, next one, please. We have one of our members in the news. That lovely image of crater Clavius down at the bottom is from the current issue of Sky and Tell, and that's from Mike Wirths, who is still a member but is now residing in the wilds of Mexico there and enjoying obviously some very clear skies there. So beautiful image of Clavius there with craters down to less than a kilometer across there. Very impressive work. I think he was our only one, right? Are we good? All right, without further ado, Al Scott will give us an update.
Good evening, everybody. So before I start my prepared talk, I just thought I'd bring to your attention something that Paul Commission mentioned. Sir Bernard Lovell, the famous radio astronomer, recently passed away at the age of 98, a true icon in the field, and was really instrumental in the field of radio astronomy over the years, coming from out of the war as an RF person. So my first item on the news: dark protogalaxies. This is a kind of a cool news story. For the first time, dark galaxies, which is an early phase of galaxy formation that have been predicted by theory to be forming the building blocks of the modern galaxies that we see today, the modern star-filled galaxies. These are earlier, kind of before first light galaxies, where they're basically just large galaxy-sized blobs of gas with very few stars, have been spotted by an international team using the VLT, or Very Large Telescope, from the European Southern Observatory. The way they have done it is they've been looking close to a very bright quasar, which is like an active core from a galaxy in the early universe, which is shooting out a whole bunch of ultraviolet radiation into its surroundings. And that ultraviolet radiation is hitting these clouds of basically just hydrogen and lighting them up like a white T-shirt lights up in a nightclub. Same sort of thing is behind this observation. So for years, astronomers have been trying to develop techniques to confirm the existence of these galaxies. They've seen small absorption dips in the spectra of these distant quasars that hint at their existence. But this is the first time they've actually been imaged directly. They used the large collecting area and sensitivity of the very large telescope and a series of very long exposures to map in the area around the quasar, which is circled in red in this image. They're looking for the ultraviolet light that's emitted in fluorescence and hydrogen gas, which has been red shifted into the violet region of the spectrum. So these are little purple blobs circled in blue on this image. They detected almost 100 gaseous objects within a few million light years of the quasar, and after careful analysis designed to exclude objects where the emission might be powered by internal star formation, rather than light from the quasar, they finally narrowed down their search to 12 very strong candidates for these low brightness objects. They were actually able to determine some of the properties of these galaxies, and they estimate that the mass in them each is about 1 billion times the mass of the Sun. So enough gas in these to form about 1 billion stars. And this is what we would consider a low-mass galaxy or maybe a star cluster in the current universe. And these were thought to have coalesced over the lifetime of the universe into the larger galaxies that we see in the current universe. So this is an interesting discovery and really a neat way to do it. And now on to the highlight of my news item, and it's been hinted at by Paul. If you're curious, it's the Curiosity rover. So Curiosity is an amazing scientific instrument. This is like the Olympics of science and engineering, but for a fraction of the cost of the actual Olympics. These people prepare about the same amount of time that athletes in the Olympics prepare to get their one event in every 10 years. Landing at Gale Crater, the Mars Science Laboratory is aimed to assess whether Mars ever had an environment capable of supporting microbial life. Determining past habitability on Mars gives NASA and the scientific community a better understanding of whether life could have existed on the red planet, and if it could have existed, an idea of where to look for it in the future. So this shows you some of the instruments that they have. There's a robotic arm here that's going to be able to dig into the dirt. It's got a whole bunch of tools here on the end of it. It's got a hand lens imager. It's like a little geologist's microscope that goes on the end of the arm, and it's going to be able to look at really close. It's got a couple cameras here, has cams for avoiding obstacles. It's got an instrument here, which is MARDI. I think it's for descent imaging. They actually took pictures on the way down. This is the first time they've actually imaged the re-entry process. They've done it a couple times now with the previous rounds of rovers. They were able to land these things, but they didn't have any feedback. They didn't have data to see what it was like during the landing process. And this is like the most interesting 7 minutes. So they've added imagers to actually help with the descent process. And the benefit to us is that we actually get images from this crazy 7 minutes. And these were relayed. They actually had an orbiter going over. They have this orbiter that they actually made it come over at the same time as this was coming in, so it could actually image the lander as it was coming in and relay the pictures back in real time to the ground control, which is really a cool thing to do. There's a mast. We know the mast has been deployed. It's got all sorts of cameras up here. It's got stereo imaging. It's got a chem-cam, which is really cool. This is a laser instrument that's going to fire out a laser and ablate vaporize rocks and then measure the spectrum of the stuff that comes off in the vapor and tell you what the components of the rock are. There's an X-ray imager instrument on top that's going to look at the crystals in the rocks. All sorts of interesting things. This is all powered by plutonium. There's a Canadian instrument on here, the APXS, the Alpha Proton X-ray Spectrometer, built by Professor Ralph Gellert at University of Guelph. Actually, and this has been on all the previous rovers as well, which has got a little radioactive foil. It puts it up close to the rock and it measures X-rays that come off the rock. tells you what's in the rock. So there's really a really cool geological package here. There's going to be a lot of interesting science coming out of this, and a lot of really good images that we'll be seeing. So this is a picture from the HiRISE instrument, which was on the orbiter going over as the lander was coming down on its supersonic parachute. This is the largest parachute ever built for a planetary mission, basically, and this is coming in at several times the speed of sound, and it deploys and it slows it down in the very thin atmosphere of Mars. And you can see, amazing that they actually got this image from orbit. Wow, really good. Here's an image from the descent camera on the rover as it jettisons its heat shield. That's a 15-foot heat shield there, which is protecting it during the re-entry process before the parachute is deployed. And you can see in the bottom left corner a picture of it being built, being looked at at JPL. So that was a really cool image too. And if you go onto the website, you can see a whole series of these images. You can go online and get all the raw science images before they're prettied up for the cameras and the news releases, and you know, look at them yourself and pick out the ones that you find interesting. This is another high-resolution image from orbit, and it shows all the debris on the surface of the landing. So you can see there's the heat shield where it landed. There's the parachute in the back shell. The Mars Science Lander's right there. The sky crane, I don't know if you know what this is. This is the rocket-powered thing that lowered the lander below it and then released it gently onto the surface and then rocketed off and crashed over there. I saw a cartoon, MSL must be really guilty about all this hardware that's leaving around. And then here we are, the first images from the lander itself. This is from the front HAZ cams just below the front of the rover, looking at one of its scientific targets, a mountain off in the distance. Here's a picture of the shadow of the mast after it's been deployed upwards. Here's a couple pictures from the nav cameras showing a little bit of the scenery in the vicinity. And you can see it's a pretty barren crater. This isn't in color. And here's a picture just to give you an idea of the size of this thing compared to the previous generations of rovers. They keep getting bigger. Got the Pathfinder, the Sojourner, and then the Mars Science Lab, which is a big monster. So we're looking forward to some interesting things to come. Thank you.
Thanks, Al. That's that chemical laser to analyze the rocks. That's an interesting device. Apparently, it can ablate rocks up to several meters away from the spacecraft, and I'm just hoping it doesn't hit any Martians that wander by, because that could be considered an act of war from the Earth.
Also destroys cats.
Also, yeah, I'd love the picture that you had there. Yeah. The laser zapping a cat. Curiosity killed the cat. You should have sent that one in. All right, Gary.
Everybody erase your minds. Look at the lasers. Erase
That's
your
right.
minds. I'll include it next month. Thank you, sir.
Yeah, bring it next month for sure.
Yeah. Okay, so here we are, finally, the leading meteor shower, or the Perseid meteor shower, and it's cloudy. But farmers need the rain. We all need the rain. I mean, we even had grass fires in town, so I know we had a lot of clear skies, but it was pretty hot then too. So here we are, the Perseid meteor shower occurring this weekend. The actual peak will be on Sunday morning at 8 a.m. With 90 maximum, 90 meteors, the zenith rate. But that'd be a nice little image too with the moon and the planets Jupiter and Venus in the morning. But unfortunately, it doesn't look like Mother Nature will let us observe it live.
That peak area, is that our time, 8 a.m.?
Yes, it is, Ottawa time. Okay. Yeah. Okay, next slide. But if it was clear, Pierre Martin, who was one of our premier observers, he's gone as far as Tennessee, I think, to chase down a meteor shower. He's been all over the place. And this is a composite of one of his images. Just fantastic. Fantastic.
Here at Atlanta to see the in December.
Mm-hmm.
Yeah.
Wow.
Deer Creek Observatory site.
Mm-hmm.
Yeah, I know, I was with it.
Yeah. So the Perseids are a fantastic meteor shower. Who's never seen them? As our meeting chair just mentioned, they're very bright even with the moon. They're moving at about 72 kilometers per second, or about 3 second driving distance between here and Montreal. So they're moving pretty fast. And some of them are very bright. So let's keep our fingers crossed, just in case. Okay, next slide. On the 13th, the next day, pretty well 4 p.m. Ottawa time, you will see the small crescent moon, and Venus will be occulted by the moon. But it's a daytime event, so unless you know where to look, it might be really hard to observe. But follow the moon, and you might be able to see it. Again, the weather doesn't look too good. Next slide. And on the 14th, after sunset, look in the western sky and you'll see two beautiful planets, Saturn and Mars, sinking very fast. But Mars is really trekking in from the west, moving east, and is just nudging between Spica and Saturn. So again, a nice digital moment. Hope we'll see some shots next month. Next slide, please. So for the constellation of the month, here we have is Pegasus, the Great Square Pegasus, along with Andromeda. To look at the galaxy, our closest galaxy, M31, huge, beautiful galaxy in the country. It's naked eye. You can see pretty well like this, the small nucleus of the galaxy itself. But for anyone that has a hard time trying to find it, I always refer to as the Great Square as a baseball diamond. So you have home, first, second, and third. Go 2 down the dugout and 2 up in the bleachers, and you'll hit the galaxy. Next slide. And we also have M33 on the bottom. Oh, can I go back one slide? Sorry. And right next to Mirage is NGC 404. I've actually put the light years of some of the stars in the area. So the first image will be M404. Very, very faint. It's it's an average galaxy, but it's near very, very bright star. In fact, you have to put Mirac almost out of the field of view if you want to catch the galaxy itself. 8 million light years away, and 10th magnitude, but because of because it's a star, pretty hard to observe. Next slide. And of course, the premier galaxy, the showpiece of any star party, the Andromeda Galaxy. Almost 3 million light years away. It's a spiral, and naked eye in the country, it's as plain as day. It's amazing to see something that far. Like people always say, with your telescope, how far can you see? Oh, with my eye, I'm looking at almost 3 million light years away, and the floors are right there. Sorry?
Who took that picture?
I just got off the internet. I think it's one of NASA's pictures. It was a NASA picture, so just no credit.
I'd say you took a pretty good picture there.
Thank you. From Barrhaven? Not really. Okay, next slide. And pretty well the distance between Merak to M31, we go down the same way to M33. It's a great galaxy in Triangulum. Just a little further, about 3 million light years away. Huge galaxy. There are many NGC objects embedded right in the galaxy itself. And these are new star forming regions, all the red hydrogen of new stars being born. And it's just under naked eye, just about naked eye in the country. And next slide. And of course the hoedown of the planets throughout the month. Mercury on the 16th will be the greatest elongation west, which means in the morning sky. You always put the opposite because it's actually on the western side of the sun. So whenever you see the west, it's in the morning. Whenever you see greatest eastern, it's at night. And of course, Neptune never moves. Next slide. And your data from last night's moon, coming up to a new moon on Friday the 17th. And of course, the second full moon of this month is the blue moon. It doesn't really turn blue, it's just the term given to it, but there has been blue moons seen through time when there are forest fires or volcanoes. The spectrum of light gets altered, actually filtering out the red and allowing the blue to come through. Next slide. So that'll be it for observations for this month. And looking forward to November is our annual dinner meeting. It will take place on Friday, November 16th, so I will have the tickets ready for next meeting. It's $42 a person, has not changed from last month, which is a good thing. And it's the same place as always, the same buffet. Hopefully he doesn't set himself on fire. It's just a phenomenal buffet. A lot of door prizes to be had. I'm just in the process now getting door prizes. And our guest speaker will be Dr. René Racine from the University of Montreal, the quest for extremely large telescopes. He's a very knowledgeable person. He's been a director at Canada France-wide Telescope and I think heavily involved in adaptive optics. So great character. I've met him a few times in 1980 up at Montmorency in Quebec. So looking forward to that night. So bring your cash. As always, $42 cash, or do take a check made out to the Ottawa Centre RASC. And that's it. Thank you.
Thanks, Gary. One announcement I should have made too. I should have thrown a slide in for this, but didn't. And I think we mentioned it last week or last month. But coming up next week is Starfest. Can show of hands of who's planning to attend there. Oh, I see a few. Excellent. Okay, so a bunch of you already know that. There are brochures available here. I know this short notice if you haven't heard of this event. It's Canada's largest star party, and we're crossing our fingers for some clear skies there. It's usually a pretty good event with a number of speakers and workshops on the go there, and it's down about 140 kilometers or so northwest of Toronto up in Mount Forest there. So if you're not doing anything next week, and you want to take a trip down, lots of cool hardware to see, lots of vendors trying to sell you expensive astronomy goods, and just a good time to be had by all. So should have thrown in a slide for that. But anyway, just thought I'd let you know. So up next is Rob Dick, who's going to talk to us about LEDs in astronomy. Take it away, Rob. Thanks.
By the way, after you finish Starfest, or maybe beforehand, if you go up near the Muskoka district, you can go to the Torrance Barrens, which is the first dark sky preserve, and that's what that picture is of. Now, which is the laser? Middle, great. And forward is?
On the right.
On the right, good. Okay, going observing for the last, 30 or 40 years, we've been using red LEDs, and that's replace incandescent light bulbs that you put red cellophane over. And that's because we want to protect our night vision. So what I'm going to talk about a little bit about that night vision, and also suggesting that maybe red lights may not be the best lights to use for most modern observing practices. So as you can see on this slide, the people use red lights. They put red lights around their telescopes so people don't trip over things. They use red lights to find their way to the outhouse, or to find a lost eyepiece that went amiss in the grass and so on. So there's reason for lights to be at an observing site. The trouble is, which one would really be better to let you see best while still protecting your night vision? Well, when you get out under a dark site, first of all, you dark adapt. And that means you don't look at any bright lights like these troopers up here. And over a period of time, your eyes become more and more sensitive to light. And we're all used to this, at least 10 minutes, 15, 20 minutes or so. The longer you're out, the better and better you see, until somebody comes by with a light, and then you kind of blow away 30 minutes of preparation. So it takes time, and because you have improvements over time. And to give an idea of the scale of it, it's changed. The way we've perceived it, or that is the way it's been described in the literature, has changed actually quite a bit over the last 50 years. But this is sort of the standard picture we end up seeing, where here we have the intensity on the vertical axis and converting that into magnitudes per square arc second, which is a unit only astronomers could love. We see that your cone vision, which is a vision that you end up using in the daytime, called our photopic for light vision, after about 5 to 10 minutes, you get a gain of about a factor of 100 or 200 in your sensitivity to light. And that takes you down to about the level that the full moon illuminates the landscape. After that, they don't get any better. So your other set of receptors in your eyes, called the cones, the rods, which are used for your nighttime vision, or scotopic vision, scoto for darkness, it carries on until literally after only about another 10 to 15 minutes, you're 2 to 3 orders of magnitude better, depending on how good your eyes are. And that's the stuff we usually always try to use. So there's really 2 points of vision. One is your photopic vision, the other is your scotopic vision. So let's see what all this translates into using funny pictures. So here we have the 3 types of receptors in your eye. Yes, there are actually 3. I only mentioned 2 earlier because one doesn't count for vision. One is called the cones. Here we are here, and this is the sensitivity or the action spectrum for the cones, and it's centered at about 555 nanometers, about 0.55 microns. And you can see it's fairly broad. And the chemicals that provide that sensitivity are very similar, and they're in the rods. So the curve is actually very similar to the cones, except it's shifted by about 50 nanometers or so to about 508 or so, 507 or so nanometers, so slightly into the green. The cones are fairly sensitive, but the way they tend to describe them is they detect about 20 cornea photons. Now, the reason why they say cornea, that's the light that enters your eye. Because you get older and older, your lenses become less transparent, and the fluid inside your eyes become less transparent as well. So they got to take something where that hasn't changed, so that's the front of your eye. And so they detect about 200. The rods, which are more sensitive, detect about 4 times as can detect light at about 1/4 the level. However, there's so many more of them that your effective sensitivity is much higher than that of the cones. Then we have these things called the IPRGCs, which is here we go, intrinsically photosensitive retinal ganglion cells. Now you know why we just spell it out. And they're non-visual. They actually set your circadian rhythm. And they're sensitive to light in the blue part of the spectrum, which is something I'm concerned about because of my work in light pollution and so on. So let's look and let's compare this with other sources. Well, here's on the right-hand side, we see our favorite red LEDs, very, very peaky. These are relatively old LEDs. They've been around for maybe, again, about 20, 30, 40 years or so. And the LED itself actually emits the red light. And that turns out to be very, very inefficient. But it works very, very well, at least in the past. But LEDs now have become literally factors of 10 to 100 to 1,000 times more bright for a given watt, or the efficacy of LEDs have become inured up to about 1,000 times higher than they were back 30-odd years ago. So here we see again the action spectrum for the cones, your photopic vision, and the rods, your scotopic vision, and the spectrum of a red LED. And I've superimposed on that the spectrum of grass. So you can see if you're trying to find your eyepiece in grass, you're going to need a really, really strong red LED to be able to find anything, because it doesn't illuminate much of the grass that would otherwise be seen by your scotopic vision. Now, if we compare this to other lights we used to use, here's the incandescent bulb here. And it doesn't give out too much blue compared to the red, but it does give out quite a bit of blue, and it nicely illuminates over the whole spectrum of grass. If you use the compact fluorescent lamps, which are being told as being great for energy, they're great for energy, it's just very bad for your health. Here's what the spectrum looks like here, kind of very peaky and so on. Very strong emission in the blue, and some of that gets sloughed over by phosphors into the longer wavelengths. And it covers a wide range in wavelengths, but when you compare it to the action spectrum of the cones, it really doesn't fit it all that well. This thing hardly gets seen at all. So another way of using it that we use, say, when we're using an incandescent bulb, you put red cellophane over an incandescent bulb and you can block out a fair bit of this blue part of the spectrum, giving you a nice red light. That's one nice thing about a nice smooth light curve, like an incandescent bulb or the sun or other light sources I'll be talking about. Because you're so broad, you can select and filter out particular wavelengths that you don't care about, that you don't want. So, Why do modern LEDs work so differently? Well, in the past, the process actually emitted the red light or the yellow light or the green light in the LED. Now they do it differently because the blue LEDs are actually much more efficient at producing light. But unfortunately, it looks terrible. At least most people don't like it. It's great if you want to look for blood stains and so on with ultraviolet light, but normally you want to see eyepieces or the scripts in our star maps. So what they do is they cover it with a phosphor, and the phosphor absorbs the light from the exciting LEDs and re-emits it at longer wavelengths. And that works extremely well. One point is that peaky light that we saw for the compact fluorescence and also with some of these blue LEDs is converted into a relatively smooth, broadband, longer wavelength light curve. So it actually illuminates a wide range of colors. Another aspect to the new ones that aren't really out yet, but they should be out in a year or less, is because when you illuminate a phosphor, the light gets re-emitted in all directions. Half of it isn't going where you want it to go. So what they do is they're going to be putting optics behind it, so the light that gets re-emitted back down towards the LED gets retroreflected and out it goes again. That'll increase the efficacy by about 30 to 50%. And on top of that, they grade the phosphor, so instead of mixing it all up, they put layer upon layer of the phosphor that produces the longer and longer wavelengths, and that increases the efficacy by another 30-odd%. So the LEDs that you see in street lights now will be obsolete in about a year. And somebody just paid $1,800 for that. So the new ones that are going to come out in about a year are going to be incredible. So they're going to be much higher efficacy, but also the phosphor is going to be farther away from the hot LED, and that means the phosphor will have a much longer life than the current ones do. Okay, so what do they look like? Well, here's a picture of the white LEDs, and this is one without any white. For example, if you convert all that blue light into longer wavelengths, you get amber. And if you allow more and more light to peek through or to escape, then that amber gets whitened. So when you have, the next slide shows you what this looks like in spectral version. Here on the top we have here's the cool white, which has a very large peak in the blue part of the spectrum and a little peak in the longer wavelengths. You go to a warmer LED and it has a lower peak, and all that energy here is being pumped into much longer wavelengths, so you have a much larger peak out here. And then that's all compared with a good old red LED. And you compare that with grass, you can see that, yeah, the white illuminates the grass and so on. But if you compare it to, but anyway, you're getting a lot of that white light coming through that is really bad for your rods. Here's the rod spectrum here, and this blue is going to excite your rods, which we don't want to do. So what happens if we convert all that white light, all that blue light into amber? Well, this is the amber light curve here. And you can see it illuminates a much wider spectrum of the grass, so you'll see the grass better. Now, and about 50% of this amber actually overlaps the cone version, or your photopic vision. So you're actually able to see much, much better than you would otherwise if you just use red. You'd use in the order of 1/10 the amount of light. Now, granted, there is some leak through in terms of it does affect your scotopic vision because about 13% of the light overlaps your rod vision. But it does give you much better ground visibility. So why should we really care? Well, there's different types of observing we do these days, which I'm going to get to. Not in this one. So with red, we have very narrow emission band, and the grass essentially appears black or dark. If you use amber, you get better color recognition because you're getting much wider range of wavelengths illuminating whatever it is you're looking at. And that also means that you're going to be able to see all the color-coded symbols on your star map. I know when I use some star maps, especially the small one from, I can't remember what it's called, from Sky and Telescope, all the red stuff disappears when you use a red light. So you get better color recognition, and about half of it's captured by the cones, whereas only a sixth of it is captured by the rod vision. So it's actually okay to use it with your rod vision. To give you an idea of color rendering, I set one of the luminaire up on the south side of my observatory, and this distance here is about 12 to 13 meters, 12 meters. And this is about 7 meters. And how much wattage you think that would take to illuminate that area? Anybody want to shout out a guess? Nobody wants to shout.
5.
Close.
1.
No.
7.
Yes. 7 watts. And that's essentially, you can run it essentially with a solar cells and a battery. Very, very low light. That's the good part about the LEDs, especially the modern ones. The ones that are in the luminaires you see out in cities right now, they're no better than high pressure sodium. But they cost about 18 times as much. Go figure. So there's good sides and downsides to not using red. Red is very good, for example, if you're just observing, because the best light you can have when you're observing is no light whatsoever. And then if you just need a little hint of light, red is really better because it doesn't touch your scotopic vision. But most people are observing like this. And the phosphor, even if you put a cellophane over your computer screen, you're still getting an awful lot of blue coming out to bleach your eyes. You really don't get dark adaptive using a computer terminal, even if you turn the red on, only red on. So it's amber is good for urban observing and also an imaging site, which most people use. And that's the one that I think we should actually try learning to use, is to have amber instead of just red flashlights, because you can use them in more. You don't look kind of strange when you're walking down a street with an amber light, and they work. The batteries will last several years. I proved it, and the new LEDs are going to be even better than that. You can just forget about batteries almost entirely. You'll probably lose it before you need to get another battery. So, and when it comes to area illumination, 1 lux, by the way, that's about 3 times the light of the full moon. That's plenty for a parking lot, for example, in a dark sky preserve. Indeed, that's the light level for a dark sky preserve. Okay, that's all I wanted to talk about. And if you have any questions, I don't know if there's time. Probably not.
We have a few minutes.
A few minutes? Okay.
Yeah.
If anybody's got any questions, I'll try to address them on topic or off topic.
I actually have one for you, Rob. Yeah. So the amber light, you say that its curve sort of encroaches into the cone curve by about 50% or so.
That's right. Mm-hmm.
Do you have any data on how that affects your total night vision? I mean, if you're stimulating the cones to that extent, does that bring you back up to like vision that you would have, say, a minute or two after you would turn off your lights?
Yeah, it depends who you read, whether the cone vision affects your cone vision affects your rod vision. And most people say they're independent. So if you illuminate your rods, as soon as you turn if you haven't illuminated your cones, or your cones are blind to it, like for example the perfect red light, then you're immediately dark adaptive. But there's always a little bit of leakage over wider wavelengths. So even the red is bound to be affecting your rod vision a little bit. And so to see something, you need very, very bright red light. But generally speaking, if you illuminate, for example, the amber illuminates about 50% of your cone vision, and it illuminates maybe or affects about 16% of your rod vision, it'll be worse than a red light, but you'll be able to use a much lower level light, and you'll also be able to see better. So if you're visually observing, you don't want any light whatsoever. But if you're going to be doing other things as well, like walking to the toilet, then you might want to have something a little bit more effective than a red light to get there. Otherwise, you might miss.
Rob?
Yes?
If it's only affecting the rods about 6 as much, but they're 4 times as sensitive, doesn't that kind of end up being sort of a wash?
Not really, because now because you're using less than about 1/10 the amount of light. So the overall light you're using in the amber is much, much lower because it's spread out over more of the sensitivity of your cones.
So you're saying you can use less light, you'll see more because of your spectrum sensitivity.
That's right.
Okay.
Are these ambers readily available? I've never seen one.
Oh, yeah, that's an interesting point. If you try to order them, they'll say they don't, at least luminaire manufacturers say they don't exist. And that's because on their order sheet, they have cool white, they have warm white, and then that's it. They don't have another box saying amber, so therefore it doesn't exist. But if you actually phone up the LED manufacturers, oh yes, here it is. They cost about $1 each if you buy onesies and twosies, and they cost about 10 cents each if you buy more. And then they cost less than a penny a piece if you buy a roll of them. And so, of course, I try to buy the roll. So, no, actually, I talk them into giving me a roll as a sample. I don't tell them, well, I tell them most of the truth.
What about commercially available things like flashlights? I mean, every astronomy store has red.
That's why I'm talking, that's why I gave this talk at the General Assembly and giving it elsewhere, and also writing articles as well. An article on this will appear in the RASC Journal, so hopefully some people will pick it up, so you'll actually be able to get amber. Because it's easy to get them. The major manufacturers have them: Philips, Nitya, Ostran. A lot of the LED manufacturers make them. Some are better, some are worse. The Nitya and Philips are about the best in the world. Sadly, the American ones that are made by Cree are terrible. They tend to be, their idea of amber is warm white. And so it's just that there's no definition for amber. And in the light pollution stuff, we've actually defined what amber is. So it's nothing less than half a micron. No emissions less than half a micron. Yeah?
If you're just doing visual observing, red is the best.
None is the best, and if you have to have light, red is better.
Light red?
No, just deep red.
Oh, deep red.
Yeah, it's strictly red LED.
Intensity.
Low intensity as you can stand, yeah.
Okay.
Unfortunately, maybe it's because I'm getting older, but the red just doesn't cut it anymore. You know, I can't see. So, yes?
Well, I'm ahead of you there, Rob, because about 15 years ago, I picked up a couple of amber LEDs from a Radio Shack at the time and put together a little flashlight because I was tired of how red made everything look flat and monochromatic color, and it was hard to read charts in general. So I decided to get an amber light, and I put a potentiometer on it so I could vary the intensity, and I found that much easier, and it didn't impact my night vision hardly a jot. So.
And in those days, you didn't have this phosphor conversion process. So the yellow light itself in those LEDs was similar in shape, a little broader, but similar in shape to the red LEDs. Now with amber, it's much more spread out. So really, the yellow ones that Glenn was talking about would probably even be better for your scotopic vision than amber, because amber does encroach more on your scotopic vision than the old yellow LEDs. But you're able to see much better, much more wider range in colors with amber.
So Rob, with if one's still using incandescent lighting and flashlights, would you recommend a brighter red filtration or a dimmer amber filtration?
I think probably a deeper red, because if you're using a typical filter, it's not a cutoff filter. And some people are in the States and in Europe are designing, even in Quebec City, they're designing a cutoff filter that chops it right at half a micron. And that's good, except they're very, very expensive and subject to the environment. They degrade very quickly. And they're very expensive. So normally what we end up doing is just getting a piece of plastic cellophane, and that's probably better. But ideally, it still lets through a lot of blue light, or because of the black body radiation curve from the tungsten filament. It's still a lot of it's getting through because of the sensitivity of your rods. So it's the best we could do until LEDs came along. But LEDs, the red LEDs, are much better. Just now, it's too good. We have trouble seeing. And if you're going to go to the washroom, I'm afraid at Starfest I'll be using amber. I don't want to miss. No.
How about traffic lights, Rob?
What, sorry?
Traffic light amber.
Actually, you hit it on the nail. That's the color. In fact, those are the LEDs. That's why it's amusing when luminaire manufacturers say they don't exist. There are traffic lights and also caution lights in trucks.
Right.
So there's an enormous market. They won't be changing that much. However, they may actually start introducing a little bit more leak through in blue. But they know full well, I mean, my grandparents knew that yellow light, you use yellow light for fog lights because it doesn't backscatter as much. That's something that's been forgotten by most people these days, that white light is actually very bad for scattering. And but they still say that white is the way to go and it's the best. Well, there's some of us mavericks that are trying to change that. Anyway.
Great. Thanks, Rob.
If you talk too long, you have to vote Eric.
That's right. I'll make it quick then. So next up we have Eric, who's going to give us an update on public outreach. And my apologies for having to bump you in the last couple of sessions there because, a dearth of material there. So without further delay.
So I get the next hour, right? Okay.
I have the advantage.
Hey everyone. Back in April, I did an outreach at Pierre Elliott Trudeau School. It's my old grade school, actually, going back 35 years. And we had a great time. First, I want to show you something here. This is a booklet. This is the very first booklet I ever received on astronomy. Published in 1971. I was about 7, 8 years old. And we've come a long way since then. In the booklet, apparently Jupiter has 12 moons, of which only 5 are named. Pluto has no moons. And but most of the information actually is still accurate in this booklet, but it illustrates how far we've come. And I really envy these students for having the information they have today. And the launch of the Curiosity mission is something that they'll benefit from for a long time. When I got this booklet, we hadn't even landed on Mars yet. And so with all the information available today, it's amazing what they can learn. But it still requires some hands-on, someone to approach them and to provide the information, to help them see all the information that's available. If we could go to the next slide, please. So before we went out and did this, I actually gave them a, believe it or not, 90-minute orientation session on the sun. We were in a classroom and I explained the basics of how the sun works, how big it is. Can we go to the next slide just to show, I think they're all out of order. If we can go to the slide that we show the sun and the earth in it.
Way beyond. You have to whip through all your slides.
Okay, sure, let's do that. Yeah, we're going backwards here from, there we go. Okay, so I created this slide actually. I couldn't find a slide that had the two together, and it wouldn't be possible to create a photo like this. But I gave them a perspective on the sun and how important it is to us. Obviously, without the sun, there would be no life. We couldn't survive. I'm a bit generous with the size of the Earth in this photograph because the Earth was about 100 times smaller than the sun, as most of you know. But they were floored when they saw this because they never associated the size of the sun with the Earth before. Next slide, please. I showed them this slide to explain some of the effects of the sun on the Earth, including the aurora. And I also wanted to add a personal touch. If you see in the bottom of the slide, you can see the Manicouagan crater. And I told them that I had been there with my good exploring buddy, Chuck. And they thought that was pretty interesting. Next slide, please.
It's your last slide.
Okay, can we go to the next one then? To the one that would be you showed first? No, sorry about that. So for 90 minutes, we talked about the theory, the size of the sun. I also explained about other stars and how there are places in the universe where it's pitch black. You don't really see anything. And that there are places where there is so much starlight, there are so many stars around that you're literally immersed in light. So to help them explain that our condition here is not the only one, that the universe is full of wonders like this. And in the classroom, we had a Q&A, and one of the students asked me,
if I was in space, could I play video games? And I told him, I said, if you were in space, the last thing on your mind would be playing video games. After the Q&A, which was very interesting, also they were floored to learn that the sun's going to explode. They all started holding onto their desks saying, oh, what are we going to do? You know, and I assured them it's not going to be for a few billion years. We went out and we started doing the actual solar observing. I want to thank Paul Commission and Stephen McIntyre for lending me their telescopes to do this. Paul lent me his Astrotech A80 with a solar filter, a +1 type solar filter, and Stephen lent me his Celestron, which has a reflector mechanism on it that allows you to bounce the light off a target. I'm sure most of you have seen that before. They were very impressed to be able to see the sun for the first time, you know, and I in the orientation session, I had explained that this is something you don't do on your own, that you need someone with the right equipment to supervise and to do this, because obviously solar observing, if it's not done right, could be very tragic. Next slide, please. We had a good balance of students, boys and girls. During the actual solar observing session, they asked me a lot of questions. They had never seen sunspots before. They had heard about sunspots, and I think they'd seen some photographs of them, but to actually see optically the sunspots for them was a big plus. Next slide, please. And my wife helped me. It's very important when you do solar observing to try to not do it all by yourself. Bring at least one assistant. I would prefer an assistant per telescope, actually. If you're answering questions and you don't pay attention to what's going on, something can go wrong. Next slide, please. So this is the mechanism that Stephen McIntyre provided, and if we have another slide, we can actually see the sunspots better in there. Yeah, there they are. More in the northern hemisphere of the sun. This device I would not bring to a young student observing session again. I found that there is a bit of a hazard in doing that. One student actually tried to stick his head in the box to look into the element, you know, and I stopped him before he did that, and that would have been very tragic. So this kind of thing I would suggest only for a larger, a more experienced group, a more mature group of students. Next slide, please. And a bit better photograph there of the sunspots. Next slide, please. So overall, it went very well. They learned a lot. It creates a basic understanding for them of our sun, and I'm doing this because I wish someone had done it for me when I was their age. No one ever approached me, us in school with this kind of equipment before, and I did it for that reason. Next slide. And the next slide. And one more. And this is a photograph I took through the eyepiece with a small pocket camera. The sunspots come out pretty good there, considering how I'm doing it. And the next slide. And I forgot to mention that I always start my presentations with our home planet. That's where everything starts from. They rarely get to see this kind of photograph. And I just love showing them that to begin with it. I also talk to them about the RASC and how they can join the RASC. That with their parents they can come down and see what we do. And it was a wonderful session, and I plan on doing these as long as I can. The last thing I wanted to mention is now when you do an outreach, you need to go through a security check, which I've procrastinated handing over, but it's a good way to ensure that when we do these things that it's the right people doing them. You know, we're dealing with young people, and I'm glad at the initiative to make sure that everything's on the done properly. And I think that's it, eh? All right, did anyone have any questions? All right.
Thanks, Eric. Always good to inspire young minds there. Some of those folks may actually wind up on the first manned mission to Mars. So who knows where the seeds that you plant when you do something like that. Good work. Okay, I just have a couple of brief slides before the break. Stephen McIntyre couldn't be with us tonight, so pretend I'm Stephen McIntyre. I'm just going to talk about a couple of things. Recent events at the Cube Gallery. They had their Nuit Noir celebration and actually managed to turn off the lights again in the middle of downtown Ottawa, which was rather nice. And apparently over 300 visitors there with a pile of telescopes on one of the darkened streets. Our Tim Cole gave a talk about Voyager 1 and 2 earlier in the week, and Rob Dick also gave a presentation on the night sky, which drew a good crowd there. I don't know if you've ever been down the Cube Gallery, but 80 people in the Cube Gallery, it gets really cozy. We also had dark sky public stargazing at the Carp Public Library on the 13th with a good turnout and a number of scopes there for people to peek through. I think we've got a couple of images there, Chris. Yeah, a couple of images from the Cube Gallery event down Julian Avenue near Wellington there. You can see the Cube Gallery itself is basically that shop there, and it borders on a street there that Wellington runs across like this, and then there's Julian Avenue, which runs down perpendicular to it, and that's the street they managed to get blocked out. So I think the next one shows some of that. Yeah, they managed to get all the lights turned off. This is a relatively small street. It's a dead end. I think that is about 400 or 500 meters long there. But having the street lights turned off makes a nice venue for folks to set up scopes and give urban dwellers a chance to see what some of us take for granted out in the country there. Maybe not quite as good, but certainly better than when the lights are on. So and fortunately they had good weather, a lot of clear skies this summer. Great. And then we a couple of images there from the Carp Star party as well there. So usually get a pretty good turnout there, and you can see actually back up one there. If you've never been out there, yeah, that's a telescope you want to get a view through. So yeah. Next one there, please. Yeah, just as night was falling there. So a good event and a good turnout again. And in terms of coming events, we have our next dark sky public stargazing event on the 17th. Now, for those of you that are going to Starfest, of course, you're going to miss that because that is next Friday. So a week from tonight, weather permitting, from 9 a.m. to 1 a.m. Again, contingent on the conditions of the sky. If that is cloudy on the Friday, then the following day, Saturday, the 18th, will be the alternative. Also, we have the National Science and Tech Week Science Fun Fest coming up in October. We're giving you plenty of notice on that, and this is really a great event. It's we want to give a lot of notice because we do have an involvement there. We can access a very large crowd. Apparently, it's very, very well attended. 3,000 plus visitors there, where there are a number of exhibits and people around to talk science, especially to the younger kids, and a lot of interactive displays as well. Just generally a good venue, and it's nice to get some astronomy in there as well. So Stephen McIntyre is looking for volunteers. If you're at all interested in helping him set out what we're going to do at the Starfest, please feel free to give him drop him a line on the email address that you see down below there. So giving you a lot of heads up there, not until October there, but there's a lot of preparation involved in pulling off something like this successfully. So looking forward to that. Are we good? All right. So next up, we have some very cool images from the members, and first and foremost, as usual, Mr. Paul Commission.
Okay, this is Berkeley 4. This particular, it's not, it looks like Corona Borealis, doesn't it? But this particular open cluster is in Cassiopeia. The thing that I wanted to tell you people today was that the Brian Skiff, a very good observer from Lowell Observatory, challenges and says that he doesn't think that this particular thing is an open cluster. Now, of course, I don't want to get in too deep and take too much time. In order to be an open cluster, as you know, the stars must be all gravitationally bound. They must be all of pretty well the same material. They have to be moving in the same direction and all that. If you really want to know, ask my neighbor here, Glenn LeDrew. He spends his lifetime studying open clusters, so he'll be able to tell you. But apparently this one is challenged. This is, a lot of these Berkeley clusters were taken, there's over 158 of them, that were taken at Lick Observatory by students at University of California, Berkeley. Some of them today are being challenged as not being true open clusters. Now, Skiff does not say why. He doesn't give the reason why he says that it is not an open cluster, but it's in literature, it's all listed all over as an open cluster. So next, please. This is Biurcon in 1. It's in Cygnus, right in the spine, just below Cedar there, about 4 degrees or so below Cedar. The Biurcon people were run by Markarian, a very famous Russian astronomer. That he was more into cosmology and galaxies than into this stuff, but this is one of their objects, very easily seen. It's Markarian 1 is about magnitude 8 or so, so you can easily see this thing. It's about 14 minutes in diameter. About 15 stars are related to it. Okay, next please. That's by your 2, which is just a little over from it, I don't know, about half a degree or something like that. It's a 6.3 magnitude, sized 12 minutes in diameter, and about 10 stars. Now these are interesting. These particular open clusters they have not been challenged, but they are right in the heart of the Milky Way. I'm very surprised that no one before the Biurcon people caught these, but these are, as open clusters are concerned, they're relatively new in being named, in other words. So that's my show for tonight. Thanks.
These are all 2008?
What?
These are all
No. They're about 20 years ago.
No, I mean your photo.
Oh, my photo was taken in 2008.
You got anything more recent?
Troublemaker.
Okay,
Thanks, Paul. That's great. Okay, Rolf's got an interesting collection of goodies for us. Rolf?
Yeah, so I call this Satellites, Planets, and Stars. What else is there, right? Okay, so this is yet another ISS crossing the sun. So last month there were 2 of these shown. I showed one, and there was another one shown. So the one that I showed last month, the ISS took 5 seconds to cross the sun, but it was very small and far away. This one only took 0.8 seconds to cross the sun. So at 5 frames per second, I was only able to capture 3 frames. But it was much closer, so it was a little easier to get some details on it. So how did I know that it was going? How did I do this? So basically, these things are predicted, and the camera, as I say, is capable of taking about 5 or 6 frames per second. So just to be on the safe side, I started the shutter about 1 second before the predicted time. So it's pretty optimistic, right? 1 second, but that's all right. It was right on, and then I stopped 1 second later, and right in the middle I had 3 frames where it was captured. So these predictions are all available on Cal Sky or Heavens Above, and it's pretty accurate. So this would have been all right. The seeing was kind of crummy because it was, the sun was very high, so it was very turbulent as well, heating up the ground. So unfortunately, the seeing wasn't that great. Still, it wasn't.
You couldn't actually
wasn't,
see it when it was crossing. You couldn't see anything when it was crossing. You just took.
Oh, I didn't bother to try and look. No, I just I have in my observatory. I have and everybody should have this. Okay, this is an atomic clock. It's not actually an atomic clock, but it receives the time signal from the atomic clock in Fort Collins, Colorado, and it every 10 minutes or so it gets an update of the time to nearest fraction of a second, and you really need that for that kind of event capture, because you set the clock on the camera and that's off by several seconds. So by the time that you're ready to take pictures, so.
Also image that on the anniversary date of.
Oh yes. Oh, thank you for reminding me. This was coincidentally the date of the moon landing, July 20th, 1969. And this, like I say, this was I actually worked from home that day because it was in the middle of the day. Okay, and in the morning, Jupiter is now visible. It's still pretty low, so this picture was taken when it was still fairly low. There have been some advances, and there's a program called WinJupos, which has been around for quite a number of years, but it has the capability of correcting for planetary rotation. So the image on the left was just a single sequence of 3, red, green, and blue, taken at about 9:04 UT. But the one on the right actually covers about half an hour of frames. Well, actually, three separate times, about 9 o'clock, 9:15, and 9:30. That's UT, so it's actually at 5 in the morning. So anyway, the point is that this program WinJupos will rotate the images and line them all up to compensate for the rapid rotation of Jupiter. And you can see that the image on the right has a little less noise, not quite as much. There's not any more detail because it was still very low. And you can see that there's a little bit of data missing here on the right because of the. This projector is not has been changed because the background is very dark this month.
Changed 2 months ago.
Yeah. So unfortunately, we're going to hopefully we'll see some of these fainter things, but they did change the projector. So it's very sad.
Too much contrast.
Okay, so actually it's not too bad. So this is the Veil Nebula, taken with a DSLR. Now the thing is, this is an unmodified DSLR, so what that means is, you see other pictures of the Veil Nebula and they have a lot of red, but the red here is fairly faint because the camera is not modified, so you can, so it picks up the blue very well, but the red is, there'd be a lot of red in here as well. So the way to get around that, I'll probably just end up taking more images. Yeah, the background is definitely not showing as much as it should.
How long was the exposure then?
I think that was about half an hour, if I recall. Which is to say maybe about 10 3-minute exposures. Because you don't take half an hour exposure, you can't do that. You have to take multiple shorter exposures.
Satellite trail in there too.
Yeah, oh yeah, I picked that up. So I didn't want to waste the precious frame, so I kept that one frame in. Oops, let's go back here. So I kept that one frame in that had a satellite trail in it. So you see at the beginning, I think I said it was satellites. So that's one of the satellites in there. That's okay. So M13. Yeah, so all right. It shows up much better on this monitor. But anyway, this was a challenge object maybe a couple of years ago. Not M13 itself, because that's fairly easy to see, almost with the naked eye. But there are some galaxies. There's actually quite a large number of galaxies in this picture, but I'll just draw your attention to 2 of them. There is this one here, which is about 13th magnitude, and it's fairly easy to see in a dark sky. So you just move a little bit. It's in almost the same field as M13. Now there's another galaxy here. And now, does anybody remember what magnitude that one is? A Tillemite. Pardon? 15. So this one's about 15.3 magnitude. It's much harder to see. And in that image, you probably can't see it very well.
500 million light years away.
Okay, good. Good to know.
An easy way to, if you want to go back to the previous one,
Yeah.
an easiest way to locate it is halfway between the cluster and the galaxy. You get almost like a Lyra.
Yes.
That's why you find it.
Yes. So there is just a close-up of it. So I cropped that a bit, and you can see it much more clearly there. So on a very, very dark night, and if you have a fairly large telescope, you might want to look for that. And I think that there's some of these other things are galaxies too.
What's interesting in
Probably
this
this one.
is you're discriminating the color between the orangish red giants in M13 and the not quite so bright horizontal branch bluer colored stars.
Yes, I guess that's more obvious in this close-up than in this one here. But it's true that there are both blue and yellow stars there, depending on their age. And also, what's nice is this star is kind of reddish, and this star is kind of bluish. Okay, this is the Milky Way, looking towards, almost towards the horizon. And besides being very colorful, it also has quite a few M objects in it. And I could probably point out some of the brighter ones. There's M22, M8, M20, M16, the Eagle Nebula, M17, the Swan Nebula, and this here, this whole thing, I am told, is M24. So M24 is either easy to see or it's very difficult to see in a telescope because it's so big. And there's this dark thing here, which I'm told is Barnard 92. So anyway, what I did was I tried to see just how many Messiers there were in this, and I put them in this picture. Oh, and Chris was able to correct something for me. I had incorrectly assumed that this was M24, but it turns out that this whole thing is M24, as Glenn LeDroux pointed out to me. So here they are. And these are all at the same scale except M24, which is enormous. You know, it would be about the size of this whole thing here on the same scale. The numbers are there. This is also known as the Lagoon Nebula, the Eagle Nebula, the Swan Nebula, and the Trifid Nebula. Not there. Obviously, it doesn't show very much detail in each of these because they're all cropped from one single picture. I'm not sure if any of the others have any names, do they? Does anybody know? I don't think so, because they're just clusters. Okay, so on another night, I took another picture of exactly the same part of the sky. Now that previous one was about a half-hour exposure, again, with about a dozen 3-minute exposures. This is just a single 5-minute exposure, so, and it was taken in twilight as well. And I was just actually testing the tracking. So that's why it's not as spectacularly colored. However, I was very lucky. This is M22, and I guess this is that must be M24. And I think that's M25. So what this is an iridium flare. And I just happened to notice it while I was taking the picture. And I thought, oh, that's interesting. I wonder if it'll turn out in the picture. And really, it couldn't have been framed any better. And I did. These are predicted as well, in addition to ISS crossings. But this one was totally random in the sense that I didn't know that it was going to occur. Now, if you look really carefully, you can't see it on this one, but you can see the entire trail of the satellite through the entire frame. actually. And of course, it's very dim most of the time. So people are very confused about this. They think that there's some iridium explosion that takes place on them, or that there's some iridium coating that does this. So it's nothing like that at all. It's about 20 years ago, when I was still involved with cellular telephones, there's a company called Motorola that was developing this series of satellites for satellite telephones, and that's what these are. These are satellite telephone satellites, and it was iridium because there were 77 of them. It was 77 satellites, and that was the atomic number of iridium. So that's why they called it that. And now, as it turns out, they ran out of money and they never launched all 77 of them. But the name is still there. So the reason that they do this is just because the panels get oriented that way sometimes to reflect the sunlight back to some point on the Earth. Nothing to do with iridium, the element. Okay, so predictions. So there's other predictions, right? So I hope everybody checks this. This is the Aurora prediction. And for Saturday, July 14th, extreme. And that's only 5. I don't know what 6, 7, and 8, and 9 would be called. 5 is extreme. Anyway, it looked like Ottawa was just at the edge of the lower limit of what they were predicting, so sure, why not? It was clear every night for the last 2 months, so why not see if anything would happen. So this was around midnight, and it was just starting out. You can just see the greenish glow starting out there. And this was at about 1 o'clock, which was pretty much the peak of the display. And you also had some other colors showing up. And then it was kind of the normal progression of a auroral display, because later on it got much bigger but also a lot dimmer. So it was a faint green glow, but it was covering a very large part of the sky, and it was also flashing very rapidly at that time. Oh, is that it?
Nope.
That's it. Oh, actually, while I think of it, I should go back here to a picture. Yes. Something else that somebody told me was that somewhere in here is Pluto. Around here, M25. It might be in this picture. I don't know. I was going to see if I could get another, through a telescope, get a better image of it. But did anybody get an image of Pluto while it was going through M25?
No, I did later, but it's actually off about here. But I was going to submit a picture, but I realized later that I did have the wrong star, and now it's actually off the frame. So it's about here now.
Yeah. Okay. So.
Unmistakably.
What?
If you look for it, it's unmistakable in the sky.
Oh, yes. Yeah, it's certainly visible. Okay, I guess, is that it?
Your picnic.
Oh, yes. Is there actually a slide for that?
Next, yeah.
Oh, okay, yeah. So tomorrow we're having the annual RASC picnic, so I hope you can make it to that. And it's also the peak night of the Perseids, so that should be something to look forward to as well. And so just bring food. We'll supply some soft drinks and water and refreshments of other sorts, but you have to bring your own food, and I'll barbecue it for you. And what else? Oh yeah, so here Chris was good enough to get the clear sky clock, and it looks like it's at the starting time of about 3 o'clock. It's just starting to clear up as well, so there'll be clouds moving in and out at that time, I guess, through the evening. if this is somewhat accurate. So it won't be pouring rain anyway. It's unlikely to be pouring rain, so that's good. Is the map there as well? Okay. So and here's the map. So and this is where we are, and so there's this huge clear area here.
Is it called the sucker hole?
So it might be all right. So I guess we're in the eye of this gigantic low pressure system or something.
There's more.
There's more. Okay. Okay. This is how you go up there. So as soon as you drive in, just turn right immediately, and you just follow the trail there up the hill because, well, for one thing, there's not enough parking on the driveway for all the cars, and then so there's a big field, and you'll just see everybody else up there. And that's that. Is there any? Oh, and there's a map. So it's pretty easy to get to. Obviously, you can contact me somehow and just take the big house. Yes, it runs from the 417 up to this road. Yeah. So you can take either the Panmure exit or the March Road exit. 6 kilometers from there. Anything else? Okay, so am I supposed to say something about the Mars thing at this time?
Yes.
Oh, okay, so they wanted me to mention, yes, so the company I work for is called Xilinx, and our chips are in that Mars Curiosity rover. And the reason is that the chips that we make are programmable, and they're not programmable in the sense of a computer chip because they're not software chips, they're actual hardware chips. However, they're programmable, which means that they can do different functions at different times, or they can be reprogrammed to do a different hardware function. So it could be controlling a motor at one time, and it can be doing image processing at another time. So you can see a number of advantages there. One is if there's any bugs in what the hardware is supposed to be doing, they can reprogram it. Another one is that they can have spares on board and reprogram them to do other functions, or they can also use less of them because they can save weight, because at one time they can program it to control a motor, and at another time they can use the same chip to do some image processing, and that's all hardware done the way it's done, not software. So those are.
So those chips that were here in Ottawa are now on Mars.
Well, actually, no, they're made in China. Of course. So it's a multinational corporation based in California, and we have an office here of about 30 people.
Great, thanks, Rolf. Okay, next up, Bob Olson.
Yep. M15 is high in the sky right now, so I decided to do an image of it. And when I was processing the image, I remembered I saw an image from 2008 with a galaxy, a planetary nebula called Peas 1, and it's sort of somewhere in here. There's 100,000 stars in this thing, and some guy in 1928, I think he was taking spectra. He was doing spectrums of these things and noticed that this one was not a star. It was actually a planetary nebula. In 2008, it was a challenge object, and I found it by freaking counting stars to get to it. And then it occurred to me that in my reading about it, it's a hydrogen alpha, produces a little bit more hydrogen alpha than the stars around it. So I took a 4-hour hydrogen alpha filter shot of this. The moon was out, so it's a good time to do that, and combined it instead of red, and then made my image, and it looked exactly like this one here now. So that was like basically 4 hours down the drain. But it had to be there. So I took the red channel. I took the hydrogen alpha channel, and I subtracted the red channel from it, the data from it, and with some balancing of it and stretching the hell out of it, I got this thing here on the M15. You'll notice that the stars, the bright stars, didn't quite cancel out, but something's there. And when I imposed this over top of the image, it was P's 1, and I counted the stars again, and it's really there. So this is an actual direct image of P's 1. Which I was pretty pleased about, actually. By the way, we have a guest tonight. Albert Sakeley is here, and he dropped in from France, I understand. But Albert was a mentor of mine at the beginning of my astrophotography career, and spent like weeks helping me do this kind of stuff. Way more than it's called. But the best thing about him was I would spend too much money on something astronomical. And the next time he saw my wife, he'd say something like, "I can't believe Bob was able to buy that Nagler eyepiece for $25. And and my wife was very gullible and believed everything Albert said. It was fantastic. M16 was in a good position image, so I took an image of it. And there's a couple of things about this that I sort of thought, this is the eagle again. The pillars of creation are in this image somewhere, and one of the things about when I show things people in my telescope, one of the things I always think about is, the light is millions of years sometimes getting to us, and I'll say to somebody, like the Klingons could have vaporized that thing, and we'd still be seeing it because the light hasn't arrived to us here. Well, apparently the pillars of creation may have been destroyed 6,000 years ago by a supernova, and they've used Spitzer data to see that in the infrared, and they think that it may not be there now, and we just won't see it for another 1,000 years. I have no idea.
How would they detect a supernova blast in advance?
Because it's probably closer to us than this is.
Yeah, if it's that far away, it would have no effect on the nebula.
Well, you're talking to the wrong guy, actually. I read this. Actually, the data that I saw, this was in Wikipedia, so it's slightly possible. Okay. This is a M39, another boring open cluster, according to Teledanko. Absolutely. This shows only part. Yeah, this is only showing part of it. What I was doing was I was just searching out the sky, and this is actually 60-second images. M71. M71 is a little bit interesting because it's not very old. It's only 9 billion years old, and it's got more metals in it than most globular clusters.
More metals.
More metals, yeah. The Crescent Nebula. The Crescent Nebula has got a Wolf-Rayet star in it that it used to be an O giant a long time ago, 4.5 billion years ago. And a few 100,000 years ago, it became a red giant and blasted off most of its hydrogen at the time. And this went off at the incredibly slow speed of 20,000 miles per hour. And then it became a little unstable, and it blasted off a bunch more stuff, at this time at 3 million miles an hour. And the 3 million miles an hour stuff crashed into the 20,000 miles an hour material and sort of blasted this sort of shape that you see. And this is hydrogen that's being lit up by the ultraviolet in this star right here. Interesting shape of material. Another boring open cluster, M52. I think I got most of this one, though. Thank you.
Okay, and next up, Gary Boyle.
Thanks, sir. I call this 50 Shades of Grey. was taken last month, almost third quarter. It's actually 30 images of 1/320th of a second at ISO 100, taken through my 10-inch f8 telescope. Okay, next slide. And did this with my Canon 450D just last week. There are 20 subs, 50 seconds each. Hopefully by next month I'll have my auto guider, so I should get some better images. The Dumbbell Nebula, so round stars. I'm pretty impressed that I actually got round stars. Next slide. And the early morning of last month, we had the show, which we're still getting now, but Venus has moved off a little to the east. We had the Pleiades, Jupiter, Venus, and the Hyades cluster. Very, very impressive. So you'll see this somewhat on the morning or this weekend with the non-person meteor shower. And through the marvels of technology, we have the image. I was able to email it to Chris during the break.
Whose cat is that?
Not mine. Not mine. No animals were hurt during this shot. Thanks, folks.
It's not real. It's not real.
It's not real, no. Magics of computers. Okay, I've just got one set of images for you here. They're all the same theme there. I've been lucky enough to be able to continue testing the new Canon 60DA. Unfortunately, next week at Starfest, I have to give it back to its owner. So I thought I'd run a few more tests before that time expires. So I thought I'd try an interesting test with this camera. So for those of you that don't know or haven't heard me talk about this is Canon's latest offering into the world of astrophotography. And I'll tell you, if you're thinking about a DSLR for astrophotography, you won't be able to do better. This is a phenomenal camera. Alan Dyer gives it a review in, I think it's this month's Sky and Tel. Is it Sky and Tel? Thank you. Yeah, certainly agree with his observations. Just a wonderfully sensitive camera, and as Rolf was mentioning, he was taking pictures with an unmodified camera, meaning that his camera has the filter over the chip that comes stock with the camera. For astronomy purposes, that's not the greatest choice because it cuts off a lot of the hydrogen alpha, the red that is so prominent in the universe. So Canon has put a special filter on that camera to permit about 3 times more of the hydrogen alpha to come through. And apparently it still takes good daytime pictures, one thing I haven't tested yet. So anyway, I just thought I'd run yet another test there that I've been wanting to do. I showed you this one. This is from the Canon D8, just with a 50mm lens, taken about, I think about 2 months ago or so. This is broadband, so there's basically just the camera with this 50mm lens just looking at the sky. But I wanted to see what this camera could do with narrowband filters. Okay, so narrowband filters, again, for those of you that may not be familiar, these are filters that we put in front of the lens or the telescope to block most of the light that comes through, except for a very narrow region around specific lines of the spectrum, specifically hydrogen alpha, oxygen 3 line, and sulfur 2 line. So these are lines of interest to us in astronomy. It helps us to identify what processes are emitting the light, and it just makes for some interesting imaging. You've probably all seen Hubble's famous pillars of creation. Speaking of Bob's talk about the Eagle Nebula, the pillars of creation done with narrowband images in those 3 wavelengths. These are commercially available for amateur astronomers as well. So what I did, this is a broadband image, and then just recently, the next one there, Chris, what I did is I took that and basically flattened the image, turned it into kind of a luminescence frame, and then took some shots with these narrowband filters. So the next one is what I used for the green channel of the image that you'll see, the composite when I put it together. This is the green channel using hydrogen alpha. The next one, this is a red channel using sulfur 2, and you can see very, very little detail compared certainly to there's the North American Nebula again there, but you can see not a lot of sulfur 2 emission there. And the previous image was 5 minutes long. These are just single exposures. The previous one was 5 minutes long. This is 10 minutes long. And then the final narrowband was with an oxygen 3 filter. You can see again a bit more illumination coming through there, and again a 5-minute exposure. What you do then is you take these 3 narrowband images, You can mix it with the luminance frame there as well and produce a color composite, just the way they did with the Hubble, and that's what the next shot is. There you go. So this is not your father's North American nebula, right? So you can see that compared to, I'll show you the broadband image here and again in a second, but you can see with the narrowband filters, a lot of the nebulosity pops right out, and the background, the numerous stars that are in this region are somewhat suppressed. So it gives you a better view of the actual emission regions there. And just out of curiosity, or just a coincidence there, that's the Crescent Nebula there that Bob showed you a much larger image of just a moment ago. So as again, this was only taken with a 50mm lens on the camera, piggybacking on top of the telescope.
Hey, Paul?
Yes.
In your 03 image, this thing showed up fairly prominently, and here we see it as a very pronounced blue thing. I'm just wondering, is that a real emission?
That's a good question, because one of the things I noticed too in the images here, and I'll just pop back there, you can see here in the oxygen, you see the lines coming off those stars? Those, especially those two. Those, perhaps, I saw Doug in the audience there, some thoughts on that. I'm not sure. These
Bad guiding.
but everything else is pinpoint.
Yeah, but they're bright enough to show, and they're only exposed for a moment.
So if it's
faint, the trails there, you just can't see it.
just glitched for a moment.
And also, those trails aren't perfectly straight. They're a little crooked, and plus it's a CMOS chips, so you won't get blooming.
Okay, yeah. That just seems like quite a jolt there.
Yeah, you probably just a second or two of mistracking.
Really? Well, actually, it's interesting because I did shoot with these on a previous night. The conditions weren't as good, so I didn't use those images. But in the 03 frames, again, I had those lines there, whereas I didn't in the other narrow bands. I'm really not sure where that's coming from.
And also, were you locking the shutter up, the flip mirror up? Maybe you were getting vibration when they fired the shutter.
Possible. You'd think I mean, the hydrogen alpha stuff is more prominent. You'd think that would be the case there as well.
You
But
don't have to boost as much to see the nebula and the hydrogen alpha as you do here.
yeah, I'll have another look at those. But in terms of your question, Glenn, I think you were looking at this region. Yeah. Battling lasers.
That's a real thing. That's something I'm not familiar with. I'm just wondering.
Okay, I discovered it.
Big, large.
Cloninger cloud.
Cloninger cloud, not a Ledru cloud. Let's see if it's, yeah, it certainly doesn't seem very prominent there. Nor there. Okay. I'm going to send out an email right after this meeting. So anyway, I thought this was an interesting thing to show you, because typically you do narrowband imaging with a monochrome camera. They're more sensitive in that, but this is the Canon 60DA, and it didn't do a half bad job. And my last slide after this one is back to the broadband. You can see the difference there with the broadband, where you're taking in the whole visual spectrum, as opposed to the narrowband there. Quite a difference in the detail that jumps out at you. So again, if you're thinking of a DSLR, this has got thumbs up. I think I'm going to have to acquire one of those myself.
How much are they worth?
They're retailing Canadian for, I believe it's about $1,800. But it can take good daytime pictures, according to Alan Dyer. So if you need to justify it or get some good PR going, there you go.
It's more sensitive to red. Why is the stuff green?
It's just because they've been mapped in, the narrowband images have been mapped into R, G, and B fields to produce a color image.
So
but
you're trying to confuse us?
Yes, I am. Is it working?
I'm confused.
Oh, then it's working. Perfect. All right. I think that was good for us there. And Tim has graciously agreed to bump his talk of Hawaii, his adventures in Hawaii, into next month, because we are running a little bit late. I think we do have time for Jim Maxwell's update on the Smart Scope, though.
It's 10 o'clock, and I need about 15 minutes.
Oh, is it?
Yes.
15 minutes?
Yes.
Oh, dear. Are you okay with that? No. I'm good. Do we have bandwidth to stay?
Sure. Let Tim go ahead. I'll wait till some other time.
How long do you think you'd be, Tim?
Maybe 15 minutes.
Six of one, half dozen of the other. Well, we have asked you to put off your talk there at, I'd really like to see you to give the update there, because I don't want to put you off another month.
Other night, because it's 10 o'clock and people are, everybody's getting tired at 10 o'clock.
I want to hear it.
Show of hands, anybody interested in staying? Yeah? Interested in staying, 10 or 15 minutes? Yeah? Okay, hopefully we won't get kicked out, so please, I'd really appreciate your presenting that. I've been waiting to hear this myself, so. That's Rolf's fault. Yeah, Rolf, you talk too long.
Thank you, Chair.
There you go. The pointer's in the middle there.
Okay.
Thanks.
Well, I'll try to be fast. I have to note that it was worthwhile waiting because I especially appreciated the talk on LEDs. Now, there's two things I learned from that. One is don't ever set up on grass. and two, make sure you go to the washroom. Anyway, that being said, again, and actually the images I saw were exceptional. I know that it's like driving my 20-year-old Ford to a Ferrari dealership. I know I'll never be able to afford one, but they sure are fun to look at. Okay, first picture. SmartScope, what is it? SmartScope? Haven't heard from SmartScope for a long time. I think the last thing we saw was 2003 in the RASC website. Well, hopefully it's back. SmartScope, the Smart Multiple Access Remote Telescope, is a 16-inch Schmidt-Cassegrain telescope mounted in a dome-covered observatory located in the Communications Research Center near the Connaught Range and in Shirley's Bay in Ottawa West. We have to keep our heads down when we're there because every once in a while we hear bullets whizzing by. While owned and operated by this club, the facility is located in a secured area accessible only by security pass. In the early days of the project, such security was not required and all RASC members had unrestricted access. Site preparation, the building of the observatory, and installation of the scope were all completed by RASC Ottawa members in the summer-fall of 2002. Details of the project can be found in the RASC Ottawa website under SmartScope. I'm going to mention a few key members. When you think they did it in 6 months, there were a few people there involved. J. Peter Williams and Chris Tarrant were the co-leaders. He keeps showing up all the pictures. J. Peter Williams was a fundraiser. If you go onto the website, you'll see all about J. Peter Williams because he was the one that started the whole idea of the SmartScope and actually had the arrange for all the funding. Oh, I should mention this is my first attempt at astrophotography. You see no stars. Doug George was a consultant for the mounts, the cameras, and the software. Doug introduced me to the SmartScope by taking me out to his backyard and showing me the identical model. Very impressive. I did touch it, though, and Doug said, don't touch it because it's clean. So I learned, don't touch Doug's telescope. Paul Boltwood was there, was a consultant. Pat Brown was a software integration, communications. Yves Demers, Richard Taylor were web design and programming. Chris was, again, designed and worked on the telescope, on the observatory. Tim Cole and Deborah Tigner were education. Ron Tolmie was images database. Hugh Pett was project documentation and the largest personal contributor and currently a member of the RASC Okanagan Center. I keep in touch with Hugh Pett. He was, I thought it was the least we could do. Mike James, Rick Wagner, Craig Quell, and Patty Graton-Bello were also involved. Now the current team is somewhat smaller. Since we have a smaller project, since most of the work has been done, Chris Tarrant is there again. He's the corporate memory. And if you have to know what's going on, you go see Chris because he's been there and done it all. Doug George, again, sitting out in the audience somewhere. Doug? He's there. Doug was is still our software expert, our telescope expert. We go for him for most everything. Stephen Norse, I think he's over there. Stephen redesigned the shutter after it kept falling off. And then there's the three new guys, Denis Tremblay, Wolfram Luncher, and me. Denis is a technician. He does a lot of my electrical work. Wolfram is just new to us, but I think we're going to get him into the software, and I'm the social coordinator. If we have to have something done, I'm the one that makes the phone calls. SmartScope started in 1999 with a call by the then Ottawa Centre President, Brian McCullough, for Millennium Project proposals. RASC Ottawa member J. Peter Williams responded with his vision of SmartScope and ideas for its fundraising so that it would not cost the club any money. SmartScope is the largest project to date ever undertaken by this club, with a budget of over $100,000 and funded entirely by donation and by sweat equity from club members. Initially, SmartScope had two main objectives. First, to provide club members with a facility that few can experience on their own. Members would be able to use a telescope that was of a higher quality than most can afford to buy, and they would be able to learn and use the CCD camera for color imaging and photometry. Second, was to provide a greater facility for enhancing the club's effort in public outreach and education. I'll do this next. I did the first one in the dark because we're all pretty well in the dark and telescope, and then I thought I'd give you the light one. SmartScope facilities, you can see, consist of two buildings, a warm, cold room, and a ventilated dome. The warm, cold room is approximately 100 square feet and contains computer equipment and tools necessary to maintain SmartScope. I am pleased to say that both heating and air conditioning function, and the wireless internet has been brought up to speed with the generous assistance of Simon Perrault of the CRC. We've also assigned 10 years of accumulated junk and mouse droppings to the dump. Who knew there was a table and chair in the room? The dome is a 10-foot diameter fiberglass home dome from Technical Innovations. It has undergone extensive renovations over the years, including repairs to the shutter mechanism from a freak windstorm last summer, an overall rebuilding of the shutter drive by RASC Ottawa member Stephen Norse, and installation of a solar-powered shutter drive. Accessories include weather sensing equipment to detect rain, wind, snow, ice, and even clouds, and a video camera to view the actual equipment, including the telescope, dome, and shutter in action. To the third one. Rather than read these objectives, I'll only make some observations. You can read them while I'm making the observations. We've made several attempts to operate SmartScope remotely, but have been unsuccessful for a number of reasons and have not made it a high priority given developmental issues. Wireless has failed, software training, and the CCD camera wasn't appropriate. All our CCD cameras have not functioned as expected, so we have installed a cheaper webcam as an interim measure until we can finish testing the site. The webcam will only allow us to do some planetary work not envisioned in the original objectives. Both the filter wheels failed and will not be replaced in the immediate future. Doug looked at them. If Doug can't fix them, they're not going to get fixed. Apparently the glass was bad in the filter wheels, both of them. The possibility of general access will depend on the reliability of SmartScope. We talked about having it open to the public. Neither I nor any of my developmental team plan on getting up at 3 a.m. to fix SmartScope resulting from a problem. Consequently, any major expenditures in the immediate future will focus on ensuring reliability and minimizing midnight repair trips. The 90% usage figure may not be realistic based on last year's experience with the domes and shutter drives. We tried to move the dome and it froze. And the shutter fell off, and we're still playing with that. We'll see. Maintenance should be low cost, but not likely until we have evaluated equipment over time and repaired with quality parts. Some of the stuff we had in there was pulled together with tape. Let's do the fourth picture. This is directly from Chris's presentation in 2001. It's in the RASC Astro Notes, 2001, AN 0102. Anyways, you can look it up. The Astro Notes 2001. The core of SmartScope is a 16-inch F10 Schmidt-Cassegrain optical tube assembly mounted on a Paramount GTS 1100S. That setup is worth more than my car. The mount, which is manufactured by Software Bisque, the makers of the well-known planetary software, The Sky, was chosen since it is specifically designed for remote use. It's a very stable mount with a high degree of accuracy for finding objects in the sky and for holding position for long exposure images without guiding. The tube in the mount will be installed on a heavy concrete base to ensure stability. Viewing and imaging through the telescope was to be done with an Apogee AP7 CCD camera which provides a field of view of 20 arc minutes. Between the tube and the camera are two 8-position filter wheels, which I've talked about. 3 filters for color imaging, 3 additional filters for photometry, a neutral density filter for lunar work, and a blank for unfiltered viewing. A temperature compensating digital focuser and possibly an A6 III focal reducer. Let's do the 5th picture. In spite of its reputation as a stable mount, our mount was completely rewired last year. That was my first project. I said, here, take some wire and open this thing up. Well, I can tell you, opening that thing up there's a lot of screws, and Chris opened it up because I didn't dare. And we collected all the screws and got them all back in. The wiring, let me just go on here. While the drive wiring was untouched, the wiring for the pair mount, there was wiring going into the mount that was again taken out of the mount on the other end for hooking up the camera and the focusers and the like. And they glitched as we moved the mount. And so we took all those connections out and ran a wire right straight through for each of the individual activities. While the drive wiring was untouched, the internal wiring to connect the computer through to the camera, focuser, filter wheels, etc. was disconnected, and new wiring ran directly through the drive body was installed. Let's do the 6th picture. George loaned us I should also put, Doug is also the equipment loaner in a lot of this stuff, because a lot of the stuff we have originally came from Doug's generosity. Doug loaned us the Starshoot Pro, but it was not appropriate camera for the long term. For now, we're using the Celestron NextImage 5 imager supplied by Focus Scientific. Unfortunately, I don't have a picture of the Celestron NextImage 5, but you can go onto the Focus Scientific website and find it there. It's designed, according to the article on the advertising, it says the NextImage 5 CMOS camera is great for live viewing or photographing the planets and lunar features. This CMOS camera replaces the eyepiece and produces color image stills through single frame or multi-frame stacking. We haven't got it installed yet. Right now we're working on our software. Doug repaired the RoboFocus this year, and it's currently in use. This is what we found when we first went into it. You can see the little pieces of wire hanging down where they taped the connections in. We had pieces of wire tape holding the stuff in place. That's all been corrected. The 7th picture, please. Filter wheels. The filter wheels are gone. They're there. We have them opened up, but we're just using them there to hold space in. We'll look at them in the future, but right now we have other priorities. Let's look at the shutter. The shutter fell off. The 3rd piece of the shutter fell off and was cracked, and we glued it back together again and put it up. Sorry, that's the shutter mechanism. Have we got the shutter? Have I got a shutter there? Are we missing that one picture? Okay, what's the next one? Let me just see this.
Battery.
The battery. Oh yes, okay. We'll try that. You saw the initial picture of the dome. Well, that broke off, and we put it back together again. But the curvature of the shutter, as it goes up underneath the second, there's a 3-piece shutter, and they all go like this on one another. And this one was broken, and its curvature was off, so it would bind a bit. We looked at repairing the damaged fiberglass shutter from last year's windstorm, but decided the $800 to $2,000 repair bill could be postponed. We may also consider repairing it ourselves, as the shutter is basically sound, but has to be re-arched to fit smoothly into the 3-shutter assembly. This is the shutter mechanism. Stephen Norris designed, built, and installed a new chain drive shutter mechanism. Incidentally, the original electric motor used to operate the shutter and supplied by the manufacturer is the power window motor from Saturn. I'm sure there are other uses for a Saturn other than supplying motors for these shutters. It works great. We'll be buying a new spare battery and charger for the 12-volt solar system. That battery is charged by a panel on the other side, and that's the only mechanism we have for opening the shutter. It's detached electronically from anything else, and we send a signal through and the shutter opens up, but there's no wiring connecting the top part of the dome to the bottom part of the dome. We're buying a spare battery and a charger for that this fall. And finally, the dome drive. Okay, this is, there are two of these drive mechanisms power the dome with a series of bogey wheels. We've had some slippage last February when we tried to rotate the unheated dome, but adjusted the tension this spring and it works. We'll be looking at brooder lights or some kind of equivalent to heat the dome over the next winter so that when we use it, it won't stick. On that February afternoon when we slipped the dome, we had planned to clean the scope glass until we found that water and detergent mix froze as we sprayed it on. Who knew? Finally, 11th picture. There's a lot of homeless mice now because we cleaned this up. We had a garage sale and we got rid of stuff. There was cameras and parts around. We finally got our tools all together. My only complaint is we only have one chair. But this is the warm room and everything's working. I'm going to talk we're doing it. The future. What we're doing right now is we're trying to familiarize the team with the SmartScope software. There's a few people who know something about a specific item, but nobody knows everything. So we're trying to get everybody familiar with all aspects of it so we won't have to rely on any one person to run this thing. We've got to install the Celestron imager. Focus Scientific gave us a cheap one, and that's what we used when we did the Venus Transit. It was a $20 focus camera, so now we have a good one. We're going to try to get that running. We're going to explore the possibilities of running lunar, sunspot, and planetary exploratory programs as an introduction to astronomy. It's great when you see these pictures, the detailed pictures that these lads put out here with their equipment. But for a new person coming to astronomy, when you see these pictures and you go to your $500 telescope and you see a smudge, it's a bit disappointing. So we're trying to give people realistic targets that they can use in introducing themselves to astronomy. We will also look at perhaps the narrated DVDs for handouts at monthly meetings. We're looking at the remote access thing we're close to it, but we've got to we'll be running some tests on our own this winter, trying so we can use it from our home. Nobody wants to freeze to death and looking at a telescope, so if we can get this thing running from our home, we'll be happy. And finally, we've got to winterize in preparation for assessing the year-round operation. So this fall, we'll be setting it up and winterizing. And that's 15 minutes. Any questions? Thank you very much. Oh, sorry.
I have a question. I was one of the original donors to this thing when J. Peter Williams came to see me. How wrong he was. He said in 2 years it'll be operating.
Oh, it was operating in 2 years.
No,
it didn't last, but it operated.
Available to the public and all this kind of thing, but it's been slow. But I realize you have all these problems. Have you any idea of when you will be able to have it operating fully?
Well, what do you mean by fully?
Well, available on the internet and all this kind of stuff.
Well, I want to know then, raise your hands, anybody who wants to get up at 3 o'clock in the morning and fix this thing if it's not working. We have the people
Well, if it's not working, you could close it down and come
Well,
next.
that's right, but that's what we have to do, and you can't make it available to the public with that unless we get quality parts and make sure the thing is running. We can't make it available to the public yet. I know what they tried to do, but when you look at the practical aspects of it, it's going to be a while we get the quality parts in it.
Well, you're going to make it foolproof, aren't you? That is that somebody can't ask for something that's below the horizon and all this kind of stuff, that the kid won't press the wrong button and make the thing spin around or something.
That's right, and that's all, and that's what we have to do in this, that's what they tried to
I
do.
mean, that's what's coming up.
But
The
the,
software handles that already. The problem we have is really more mechanical. If the shutter fails to close, we have a crisis situation. We need to protect the observatory from being damaged by weather.
Oh, okay.
So that shutter has to be absolutely reliable, and that's really the bugaboo here. It has to work.
Oh, I see. You can't get the security guards to come and close it, eh?
They'll call us and tell us it's broken.
yeah, no, that's,
What happened when the wind blew it off?
we're a volunteer organization, and we have to not abuse our volunteers, because if we abuse them, we're gonna lose them. So that's the kind of stuff we have to think about. And so that's why we're taking our time and putting our money into the quality parts and not worrying about the fancy stuff right yet. Anything else, folks? Well, thank you for your time and patience, so appreciate it.
Okay, Estelle, I know you're here. Estelle's pick of the month, binocular astronomy. So if you're interested in perusing the sky, especially in the summer now with the Milky Way prominent, probably a good book to have a browse through. Just again, a quick reminder before we close. If we get the skies, check it out. I get the feeling that if we do get the skies, this might be a very nice occurrence of the Perseids coming up in just a couple of days. Again, and one last reminder, Friday, August 17th, next Friday, public star party at the Diefenbunker, weather permitting. The rain date is, or the cloud date is August the 18th. And our usual closing slides there. Estelle with the library, Hal Scott, I don't know if you're still trying to unload telescopes. Art and Ann Fraser are back this month, and so if you need coffee and refreshments or our RASC membership information, please go and see Art. Stephen is with us tonight, and a reminder that the rest of the museum is closed, and for those of you that would like refreshments afterwards, we have our standing reservation at Kelsey's. 82 tonight, a little bit on the light side, but summer's calling. So thanks again for coming, and thanks to the Museum of Science and Tech for hosting us. Again, my email down at the bottom of the list there. If you have any submissions that you'd like to send, images or proposals for conversation, or for presentation, just drop me a line there. And a reminder: our next meeting is Friday, September the 7th. At 8 o'clock, so our usual time and place. And I think that's it. Thanks for coming. Enjoy the rest of the summer, and we'll see you in a month. Thank you.